I think we will continue with two presentations, one from me, from Riga Technical University, another from colleague. Also will come and I will very shortly show, because I have little problem with my health and not possible long time to speak at this moment. But I will show what I'm doing and what is my connection with remote sensing. Today we also celebrating 160 years for university. You also see a lot of the people inside, outside. And yes, we are oldest technical university in Baltic states. About me, I think 80% know me. I will not a lot to say what I'm doing, but maybe something don't know what I'm doing more, and I'm working in different fields, but all fields is connected with digital twins, and we can see digital twins from underground to space, and that's how data is come together. But also I'm working with some technologies connected to VR technologies or augmented reality. I think these technologies also will come in ESA and space, and it's come in ESA, but not in application to detect the land or marine, but in application of satellites. Also, I'm working some fields like the hobbies, but at this moment it's not come to hobby. Last slides I will present how to use satellites image in culture heritage field. That's something different from land detection. And that is very shortly about me. I'm also working in two universities. The base university is Riga Technical University, but we have one study program together with Vilnius Gediminas Technical University, and some people from this room also finishing this program also in Vilnius and Riga. That's yes, some small slides about Riga Technical University. We have 11 study direction, and together up more than 137 study programs. Study programs is changing every year, little more, little small. But I am come from civil engineering, from geomatic fields, but also in this building, computer science and information technologies. Also, I doing some projects, and one project is connected with garden plant and multispectral cameras to detect the some damage of the flowers, and to see is it very nice flowers or not, and to search some application that's connected with Latvian University and Agriculture University. Yes, also this week you see a lot of and hear a lot of the lectures, and some people asking about Pythons or Jupyter or another, and that is connected also lifelong learning. Every time we must to see what we need more to learn, and in our university also a lot of the course come to mood type course that's similar like the ESA or another institutions. You can find a lot of the courses. Some courses is free, some courses will maybe lead to pain, but this lifelong learning is especially nowadays is very important, and that's the science part. Yes, research platforms in university. We have 6 main platforms that's connected, and also you'll see this environment platforms where under this is also going this land climate change, and another is also in cities and development. But also is I'm little also under security or defense, working on transport. That's and 2021 university also in summer signed this agreement with ESA, and also this course is connected with this agreement, and we yes, technical university increase the development of the research, innovation and industry. Before lunch, you will see this from Poland, this colleague, and also said about this industry. And that's we go inside, and we have projects before also this signature connected with some materials of the satellites to analyze some also application or another. If we looking from view from Riga Technical University or Latvia, and some users or scientific researchers in Latvia, last year Ministry of the Education and Science have this analyze of the situation in Latvia that is published and public in website also of ministry, and the aim is of this study is to analyze the situation in Latvia regarding the possibilities of using the data Earth observation program Copernicus, this and also global navigation satellite system Galileo. But ESA have a lot of the programs, but this analysis come only in these two parts: Copernicus, Earth observation program Copernicus, and the Galileo program. In this, I will not show all this report. You can see this report in website, and but 27 organizations is identified in this analysis who are users and also research companies or institutes, and also 3 education institutes. But from this year is 4 education institutes. It's come Riga Technical University, Latvian University, Ventspils University, and Life Science and Technologies universities. Also is going in this remote sensing part and use this data from observation. And yes, and the main goal, the in this report is analyze a lot of the users and or fields, forestry, agriculture, or another emergency management, or all. But the main some part of this results is what is study demonstrate is generally organization have a low level of the using data. That's normal because we need the high resolutions data for works in Latvia, but also this show we must to go in regional research parts in to see around of the Latvia, not only inside, and that's maybe is a goal for research institution to go deeply, to go more projects in ESA and working. And our colleague also said in September will be this some parts from ESA for researching also. If we come back to Riga Technical University, we have a lot of the study works or final works and also some research works. The main goals is going to Galileo, a lot of the research to Greenness systems and how to use this data, some algorithms, but also every year we have 2 or 4 final works to connect and reach Copernicus and Galileo, where students are studying some innovations or some problematical parts. Yes, and most of the works is connected by food or land detection, but also it's come to some, you'll see also the measurement of the sea surface and wave height using this Galileo, also not only like the Sentinel 1 or Sentinel 2. Also is connected with well-being techniques in geodesy, how to research this space or another one. And yes, if we come deeply in all departments, we have 3 study programs connected, bachelor and master study program, and also together with Vilnius, Gediminas, we have innovation solutions. There also you see some example how students are studying and publishing in web to use GIS systems, not only like the PDF or PowerPoint presentation, but put algorithms together and then move and analyze. That's I will not go deeply about this project, but that's also. And in all courses, we including everything what you see here in this week. Also including the basics, also including data analysis, Pythons, MATLAB softwares, SSNAP. We have very nice cooperation with S3 and also sometimes with hexagon groups from ERDAS imaging. And students are learning how to create these algorithms, principles, and also publishing the results, because that is important for we present. And no, sometimes I'm go deeply and there I put the one slide. On the first lecture I show this Tucker researching of the longer time researching about this part, because in this is coming 40,000 data in satellites, orbits of the satellite data inside, and if we short time analyze, we cannot see the climate change or everything, and that is also important to put together another data set, Copernicus data sets, because Sentinel 1 or Sentinel 2, Sentinel 3 or 5 is not only data from ESA or Copernicus. We have a lot of the data sets, what we don't discuss in this week, because that is another part. And this Copernicus including all. And in this year, this week, I'm discussing with some from you, with some people of this course, and we must know most of the things, mathematical, physics, or orbits, space, biology, or meteorology, or another. That's not possible for one people. We must organize a team. Some people are very nice working with application. Some people with Python or data sets put very fast. Some for publication, but basically for students we give some parts of this all. But in research fields we looking for the teamwork, and then looking for the around, because we are open space people, so you can looking at everything university in Europe for research, and then is sometimes I use also this Copernicus database, Copernicus data stores, and this is very, you can see in this page, and you can find some data sets from climate change. Climate data stores also use the API. But what I like in this page, the page is sometimes changing, and something is there. You also see some problems in this page, but that's not important. But what I like in this page, you can see, and you can download and see some timelines from analyze, but also very nice part is this Python part. If I don't very high level Python people, I can go there and I can put my blocks together, and there you can see this Python code and also run this code. And if you are understanding Python, you can editing and put some new class or libraries inside. Libraries maybe not possible inside, but you can define new class and put new algorithms inside. And that's also is demonstrated the results of these two books editors. And you can take the data and put together and show. And also this application gallery. I show only an example from climate data store, but also you can go in land data store or another data stores and also found some data what is put in the database, and also some applications inside. And yes, this I like in this Copernicus data sets. I can put, and I can put some my coefficients if I need, and that will analyze the data from this, or put my data inside, and I can use. Another field where I'm working is culture heritage field. I 2 weeks ago come from Ukraine and come from culture heritage, some damaged territories. And there is one example, not to use Sentinel 2 or Sentinel 1, but in the ESA have third-party missions. If you have this some project, you can ask for another satellite data, world view data, or another. This is not doing by me. This in the public website. UNOSAT doing in around of the world. This service creates some reports of the damaged territories, damaged culture heritage. This is from Aleppo, part in 2049 and 40. You can see this, if I remember, worldview satellite using is, and this is Palmyra. If you remember, also is full damaged. This city And also you can see how to analyze. This is a final report, and but also it's preliminary reports that is not going on the field and see, but they put some fast results. That fast results is come from Ukraine, also from Chernihiv. Almost I visiting this Oblast region. I speak in Ukrainian language also, but okay. But this is not checked on the field. You can see a lot of the damaged territories, some 900 places, and after that is one later crater. This is later crater, and then also checked, and some place where I'm visiting, it's looking like this, and you can in the satellite data found. There also maybe it's possible to use Sentinel-1 also, because this place is a big place damaged, but the fast results is used by visually from this. This also not created by me, that's from Unitar created. But that is another view how to use this satellite data and in another field, not only to check the some. And I said ESA has these third-party missions, and also some people who use S3 software, so they know it's possible to get this directly access, but you can ask for ESA this access, but if you have this project and project is accepted, it's possible to get this access, and you can use high precision, high resolution satellite data from third missions, party missions, not only Sentinel missions. And there is a future featured missions what is possible also to use, and in this last damaged territories, I use Worldview 4 image and visualize, analyze this, but there possible another missions to found. And yes, this planet scope also, you see the scientists go to Earth estimate, and also this planet scope data also is get access from ESA if you have project and you have use higher resolution data. That's also if we looking for some projects in the future, you can understand this Sentinel mission, but you also we see this reference data. We need some more accurate or more higher resolution, but maybe you can looking on another products in the ESA node and see. Riga Technical University also not working for application, but also working for the structures of the satellites analyze or another, and they are looking for another project types, not only application. And in 1918, yes, this sandwich structure analyzed for assessment of the damage resistance that's important for satellites in height or strange territory. Another project I will not talk more about this is food analysis in Uoga city in Latvia, where we use this, some open source tools and data, but there also analyze this ice place in the river in spring. That's created algorithm by Andres. The author is also here, and that is a web platform in the Cesium to put on all data, three-dimensional data, LIDAR data, and drone data together. It's a basic algorithm this analyzes food analyzed from river data, but also it's possible to some ice detection also from Sentinel-1. If you have about this some questions, you can ask Andres, but not to me. And yes, that is very shortly about from me, from Riga Technical University. In the ESA, another faculty is also something doing for electronical, for materials, or another, not only for land detection or Sentinel-1 or Sentinel-2 or 3 or 5 data analyze, because we are technical university. We must looking in every space what is possible. Yes, that is all from me.
Thank you. If there are any questions, you can ask while I'm switching presentations.
Okay. No questions. Because everybody may know, and then I think it's, we can discuss every time. Okay, thanks.
Okay. Then let's go further. My name is Dainis. You have noticed me here announcing something and so on. I am representing here the Institute for Environmental Solutions. And today, when I was thinking about what to say, I decided to make the presentation as lessons learned while working with Sentinel Data. And our experience working with Sentinel Data is dating from, I don't know, 2015 or even like earlier and so on. We have done different studies and worked on different applications using Sentinel Data, and I will share some of them and also give you some kind of advices what to do or what not to do if you want to try to do something. And okay, let's move further and a little bit shortly about our institute. It's a privately established research and innovation institute. We are located near Cēsis in the airfield. We are combining different disciplines, starting from the technical ones, also covering disciplines like expertise in forestry, agriculture, ecology, and etc. And our two key focus areas which are related to this course and to these topics are data-based environmental solutions and Earth observation remote sensing. In case of remote sensing, we are working with different type of platforms, starting from satellites, going down to airplane, acquire data from airplanes, also drones, and also using quite a lot of different sensors on the ground. If talking about Sentinel data, there are some points what we can just kind of highlight. And as already, those who are just, I understood you have like different experience with Sentinel data. Maybe for those who are more experienced, it will be some kind of repetition of basics. But I believe that these are some points which is quite important to point always, that there are 2 points of Sentinel-2 data, basically, optical and radar. And if we compare it, I usually like to compare it with like, this one is like a very nice, colorful TV, where you can get nice images and look at them, and this one is like a black white TV with a lot of noise. But the difference is that there is always that you will always have problem with availability of useful data due to the clouds. And as we are living in the northern region, the cloud problem is like more and more, let's say, not important, but more frequent. Frequently will appear. In case of Sentinel-1 data, on first view, it could look like as really noisy data with something like blinking and so on. But the main advantage is that you always will get this continuous data flow. At least these satellites are working in orbit. Previously, unfortunately, I should say previously, we had like 6 days repetition rate with 2 Sentinel-1 satellites. Currently, one is out of operation, and it means like now we are on this 12-day repetition rate, but in future, I think soon, we'll have this 6-day repetition rate. In case of optical data, the repetition rate is also similar, like 5 days. But what is also quite important to know that we are living in north, and as all satellites are flying basically from like in that direction, it means there is like overlap of orbits. It means in each point you can look at the data not only like from one orbit, but from several of them. For example, in case of radar data, it's usually there are like data from 4 orbits are available, like do ascending, do descending. Basically, it means like from each orbit you can get, okay, I would not say 12 days. There is some kind of difference, like in data acquisition rate, what appears, but basically it's quite a lot of data. And the same could be attributed to Sentinel-2 data. There is also overlap of the orbits. That's why we have even more higher frequency of data acquisition. On one hand, it is like a plus, but on the other hand, like you always should deal with the clouds. And this is something what you cannot predict. And this should be taken into account, and there is like usually like this decision to make, like what to do. Like for example, if you have like cloud-free image, of course you can use it. But for example, when it comes to such kind of images, like are we going to use this part of image or not? And we will look for cloud-free image, etc. Another aspect when working with Sentinel data to keep in mind that there is this spatial resolution. If you look in total, like in Sentinel data, basically what you should know that I would say it's the state of the art of freely available data. Basically, European Space Agency, I would say they are just dictating like what is the best data for free available. And basically those who are commercially providing data, for them, there is no reason to provide something similar. You should go somewhere like more in advance. And basically, currently, if we're talking about freely available data, I would say like if you want to work with like all the spectral channels and radar data, I would say that resolution with what you will end up will be like 20 meters per pixel. This is what you can see in 20 meters per pixel. You cannot distinguish some kind of small objects, but for example, for relatively large or small scale change detection, it could be accessible. Basically, from this image, you can somehow say what's where located. But also, if the pixels are quite large, it means the information within these pixels is mixed. Basically, it will be a mixture of different land cover types. Then, for example, 10 meters pixels, and this is something what you can get from the Sentinel-2 optical, like basically RGB bands and also one infrared band. It's usually enough for quite a lot of studies. Basically, this is something which is like, I would say, the best currently available data for free. And then, of course, if you want to go higher with some kind of high resolution, like 1 meter or below 1 meter, then it's like other like commercial data from commercial satellites, airborne platforms, and etc. And here is also some quick comparison. What means like 1 meter data, which is usually used when it's going like talking about higher resolution, and then it's like 0.1 meter data, like what kind of objects you can distinguish. And of course, if you want further go to some kind of like really high resolution, I would say then it's matter of drone. In this case, you can get like pixel resolution below like 1 centimeter, like which counts maybe even like in millimeter or something like this resolution. And then you can count flowers and separate plants, etc. Not from space, but from air. And then I was thinking like what kind of examples to put here from our previous experience, and I decided to just look at one example on which we were working. I think, yeah, it looks like 5 years ago. And why I took it out, because we are usually also going to this event which is called like Living Planet Symposium, which is held like every 3 years, like large conference where you can get like an update on like what's happening around in Earth's observation field, like what are the new trends and what everyone is doing and what accuracies are reporting and so on. And like quite interesting thing what we noticed that there was event in 2019, and then like it was time when satellites were in the orbit for a while. And it means that everyone had the chance to work with this data, produce some kind of results and so on. Everyone was trying to show some kind of results with like higher accuracies and so on. And this example is about like agricultural lands classification and different crop types. And this is one of thematics which is, I would say, like top thematics for Sentinel data. Because if you look at the application of the Sentinel data in like basically case of land monitoring, I would say this agricultural field is the one where it's the most useful, just because of like radar C-band. It is like it's more useful for agriculture rather than, for example, for forests or other land cover types. And of course, that's why one of these like targets is this just cross-check of agricultural lands and so on. And what we saw that in 2019, everyone tried to report like accuracies, which is like 95%, 98%, and so on. You're just looking at these accuracies like, whoa, this is something what we should reach, and so on. And then this year conference, when there is like 3 years have passed, you can see that the average accuracy that people are reporting in the same field, like working on the same thematics, now is like around like 80%. Why it's so? It's just because time has passed. It's just my interpretation about like why we can see such kind of drop in accuracy. It's not because of like the weather was not so good anymore, we had less data, etc. I would say that it always depends on the scale of your experiment and what you are testing. Like for example, like your algorithm will always work better on the local scale rather than larger scale. I suppose most of the studies just were based on larger scale, even like on country scale and so on. In this case, your accuracy is not anymore. It's like 90 with something percent, etc. And then also what we can see in the shift in evaluation of accuracy is that the way how it's evaluated basically also has shifted. And I also think that it's somehow related that these developments, they went closer to the market. Basically, those who 3 years ago were reporting 98%, they were not actually working with customers. But when you start to work with customers, the same like paying agencies, yes, you can see like what is the real accuracy. And that's why it's very important from beginning, in my opinion, just to look quite critically on result what you can get. Look at not only trying to get like the highest accuracy, but understanding also the limitations. Because Sentinel data, what I said, it's like really good. It's like basically the state of the art of freely available data. But we also should understand that there are limitations. Limitations in data availability, on what you can recognize from this data or classify or at all, what you can do. And that's why I just took this example again because it's quite interesting. If you want to use Sentinel Data for classification task, I think it's like really good exercise to work on, because in this case you can try different strategies and different combinations of data and look how the results will go on and so on. Basically, this is a region of interest that we were working on. We use both Sentinel-2 and Sentinel-1 radar data. These are the main crop types in this region. Basically, it's more like grassland covered region, around 50%, and there are some other crops. We just took some crops which are, you're pretty sure that these are crops with some kind of, should be at least with some kind of significant difference from the others, and for the study, and it looks like something maybe 10 or a little bit more of them. And here it comes. Let's look at the accuracy, what you can get if you use optical data. What was interesting with optical data, this was 2017, and 2017 was really bad year for optical data, at least in Latvia. If you would check the archive, you will have a lot of cloudy images, and I think that in case of Sentinel data, maybe we should introduce something similar as, for example, in this wine market, you always have this, this year was good for wine, this year was bad for wine, and so on. The same you can kind of reflect to remote sensing data, Earth observation data, and 2017 wasn't very good for optical data, because if you look at the region at cloud-free stands and so on, then you can find something in spring and something in late in summer. And basically, this is something which you already can understand, oh, it shouldn't work out well if it comes to agricultural classification, and we already can see it from the accuracies over here. Our goal was to reach 85% accuracy per crop type, and what else? It's interesting always to look at the errors, basically, where they go. And if we look, for example, at these crops like 111, which is summer wheat, which is usually misclassified with barley, summer crop, and also oats, also summer crop, and similar trends you can see with other crops. Basically, what you can see, if you would put together all summer crops and all winter crops, and also, for example, if you would put together these permanent grasslands and cultivated grasslands, you would get quite decent accuracy. It just shows you that this data set isn't enough for distinguishing between these all these different type of crops, but it's still quite okay to read information about which crop is winter crop or summer crop, and also distinguish between crops and the grasslands. And this accuracy would be very good together, because when you look closer and trying to understand what is real difference between permanent grassland and cultivated grassland, actually in reality there could be no difference. Basically, what you're trying to do, you're trying to classify two relatively similar classes, just basically train an algorithm to distinguish between classes where there might be no difference. Basically, this is something by logics goes wrong to do like this. But okay, let's go further and check. In case of radar data, we tested not only one orbit, but two of them. And what I also can say that it's not that you can take each of the orbit and the result will be the same. Basically, the result might differ depending on the orbit. Which is better? In this case, this 160 orbit, which is a standing orbit. Sometimes you think that, okay, this orbit should perform better, but at the end it turns out that the other one is performing better. But this is also something to take into account, that there are more than one orbit to work with, and there is always possibility to use one of them, or to work with like both or all of them. In some cases, there are even like 4 of them are available. But if you look at the accuracies, just using only Sentinel-1 data, and in this case, of course, we use like all available data set put together, and the accuracy is like significantly increased. In some cases, they are over we're over this 85%. And for example, rapeseed, these are crop types, which is like really well distinguishable from Sentinel-1 data. This one also, it looks like, but it's not just because it was distinguishable, but we can see the errors, like all the others were classified more and more as barley, and so on. And it's still like looking at grasslands, we can see the same picture. And here is the result, what happens when we put together like optical data and with radar data. And you can see that when we look at the accuracies, they significantly increase. In a lot of cases, they just overreach this expected 85% accuracy. Still, in the case of grasslands, you cannot distinguish them. You just already mentioned why. And still, we can see that there is some kind of misclassification between, for example, this and these, which are, all of them are summer crops. And I believe that it's just because of the lack of these optical bands within the particular year. And what happens when we combine these two classes into one, we can see that this accuracy goes up like to these. But of course, I should mention that we should look quite carefully at these accuracies, like when performing these tests and reporting them. But in this case, I wanted just to demonstrate like how separately these data sets work and what could be the benefit while combining them. But in case of grasslands, what we can see is that most of the job is done by Sentinel-2 data, and only like small kind of improvement is introduced by adding radar data, because when looking separately, radar data is not performing so well if compared even to Sentinel-2 data, which is based only on two data stands, like from spring and late summer period. Basically, this is always when you start to work with Earth observation data. These are experiments what you can go through, test like which data is better for your application, because this is very important to understand. Like lesson to take, I think, from this study is that each of the data sets can give some kind of advantage to the result, as we saw, and it's very important to understand looking at these experiments, like what exactly each data set allows you to classify or recognize, and then putting together like what is the real advantage of each of them. And this is some kind of visualization of this experiment. It's actually from experiment which was like year before, but basically what it shows, it anymore doesn't show like where there was no like mismatch, but this mismatch is demonstrated in form of probability, basically. And what does it show over here? That this part was like declared as in reference data as a permanent grassland, but we already can see from reference data that it was plowed, and it's more like this type of crop, and basically that's why it was marked as an error, and it highlights. And this is also an example about what I want to talk, and I will talk quite a lot, that how we represent the result. Because in the representation of the result, there is always two ways, at least in this Earth observation. Basically, if you have a question about like what kind of land cover it is, you can answer it as like, for example, it is like grassland, or it's like it's not grass. Basically 1, 0, yes. But there is always possibility to provide your result in frames of probability or confidence, some kind and so on, some kind of not like 1, 0 answer, but in frames of, okay, this is like grassland with like probability, I don't know, like 85% and so on. This is a result, this is the way how you present result, and later I will tell why it is so important. And why it is important, for example, in this case, within this study, during this Living Planet Symposium, there was also quite an interesting story from one foreign company which were working with their national paying agency. They got the result with accuracy which was around like maybe 80% or even lower. They were thinking, okay, it's not like really good result. But then they approached the customer and asked them, okay, in a standard manner, like what is your capacity, like with how many cases you can deal? They said, okay, we can deal like with 5,000 cases per season. They said, okay, it means like, because if you look in total, for example, you process like all countries, yes, you will get like, I don't know, like a million of some kind of misclassifications and so on. Within them, there will be some kind of true misclassifications, which are related to some kind of violation, and there will be some kind of false positives and etc. But in this case, what they did, they just ranged all these results, all these cases of misalignances, like with reference data and classification, according to the probability. And if you do so, usually if your algorithm is logical and it's performing well, then on the top, there most probably will be like true misclassifications. And then just provided them like these 5,000 more significantly like visible misalignments. And what was the win-win story is that this is the way how you can cross the gap between there is always like user with its expectations about the result, about what they want from the data, and there on the other hand there is like data result with the limitations what you can reach. And if you ask me like about such cases, like what is like the real accuracy what you can get from Sentinel data in application of agriculture, I don't know. I would say I have seen reports 3 years ago going to 95 and up accuracy, and now I see reports going to 80% accuracy. I believe it goes like something like this. But I also believe that it's not like the true accuracy is not like 95 or up percent. It's somewhere maybe close to 90 what you can reach, and etc. But it's always, on one hand, of course, you can go for high accuracy, but on the other hand, it's always important to understand like how this data can be used. And I believe that Sentinel data and these data products can be used for every end user, but their kind of compromise should be found. How? This is another example from the same activity project. Actually, we were working not on these agricultural thematics. Actually, we were more interested in grasslands monitoring, and that's why the focus main was on grassland classification, classification within the landscape, and also separation from other agricultural lands. And here is an example how you can check for management events in the grassland. In this case, we used radar data, just because we were interested in higher frequency, the highest as possible, and radar data is quite useful for detection of plowing events, basically. Of course, if you need like lower frequency, if you don't need like really high frequency in management, sometimes it's enough also using optical data in such case. We also did a joint study with Kappa Zeta. It's an Estonian company. There is one representative for Kappa Zeta, but he is not here in this room now. But it's a detection and management of activities like mowing. There is mistake. And then plowing events in grasslands using radar coherence data. Basically, it's the same what you did yesterday. from the same process, you can get coherence values and then also analyze how they are related to some kind of changes on the grass. Basically, if we look at the basics, why we apply coherence processing, so that vegetation usually has low coherence. If vegetation is higher, the coherence is usually lower. But when vegetation is like low or sparse and so on, the coherence increases. And it means that after plowing, you can you have like quite stable ground, basically transparent, etc. And you can observe coherence increase. But of course, for calculation of coherence, you need these two measurements to compare it. And it means that you will be able to detect some kind of event only just after maybe event and then two measurements and etc. But still, for monitoring of if there some kind of management activity has happened or didn't happen in grassland, it is useful. And Kappa Zeta is, they are expert in this field, and they are also providing it as a service, as far as I know, to Estonian paying agency. And if someone from you are interested in this, then I would encourage you to contact them. They are experts in this field. What also we tried in these activities, which I think it's quite challenging. We tried to map invasive species, and the only official invasive species in Latvia is giant hogweed, Heraclum sosnowski. And the territory where I'm from, where I'm an institute from, is very well known with giant hogweed as almost the crop type, because you can find fields 100% covered with giant hogweed, and this territory is really good for such kind of studies. What we did, we just tried to we performed tests how useful could be Sentinel data for mapping of giant hogweed spread, and the conclusions out of it, of course, this territory was really favorable for this demonstration. That's why we reached this high accuracy. But the main challenge is in relation to giant hogweed, particularly that, of course, there is spectral difference, what you can detect and rely on, but it also the species which is usually really intensively controlled and in different ways. It could be cut, it could be fight with some kind of chemicals and so on. And it means at certain point it appears in different spectral colors, because if it has been controlled by some kind of chemicals, it starts to become yellow, etc. And this makes it more complicated in these cases. But what we saw for some kind of large spread of hogweed, Sentinel data still could be applied. Just looking at particular specific moments, and to track at least some kind of suspicious areas. There also you should expect that there will be false positives with the plants which are similar to this one, but still, if you want to get quick overview, what is the change, for example, this territory, this is something which is really affected, and there were really dynamic changes. And at one year you can see that hogweed has been in this field, and it's somewhere over there, and so on. We saw that for such cases it's quite useful. And also the main limitation in using Earth observation data, you are looking from the top. And this invasive species, it spreads around roads and river banks. And river banks, they are usually overgrown with trees. And what you cannot see through trees. And also there is minimum measurement unit what you can detect. Basically, what I also want to say that it's more related to some kind of control of large fields, if they have been infested, have been properly managed or not. For spread detection, I would say the different spread basically modeling, different approach in my opinion, should be used. Another thematics we have worked on, it's of course related to forest monitoring. We have been involved in these activities. Here you can see results from yearly monitoring, which is sometimes interesting for some end users. And this can be done with optical data, because if you want to get some update on forest cover on a yearly basis, yes, optical data is useful. Just wait for full archive, use all optical data. In some cases, you can even do it like from one optical stand and so on. It depends on the case. But of course, if we want to go towards like more higher frequency monitoring and start to use optical data, then you look at the archive and use something like this typically. Basically, yes, this is like the nice part of optical data over Latvia. And then you are thinking, okay, how I can use this for forest monitoring and so on, or for at least not only forest monitoring, but for higher frequency monitoring of like any kind of land cover changes. And then you understand, yeah, it looks that we should try radar data, because at least radar provides you with continuous data flow, etc. And this is example what you can get from radar data. Unfortunately, I didn't have time to make some kind of nice presentation like how radar data in this case looks like, and in comparison to optical data, but I will try to explain. Basically, you will now see like that something is painting on. In this case, there is like date. We're just generating such kind of video just for analysis of each cases. I just took one of them, and here is some kind of information about this. The clear cut was done like 15th of September. Basically, we're zooming into this is digital object model, basically to see how large are trees and calculate this canopy cover, etc. Then we can see how this changes, and when we detect clear cut, basically. We started detecting it from here, and then we just continue detecting it here. And it looks that if you look at this example, it looks that clear cut somehow starts on like this 15th of September. It is started from here, and then it goes like this, and it takes approximately months to cut these trees and so on. But it's not the reality. What's in the reality? Basically, this is how you can detect clear cut with radar data. But with radar data, you have like, because with optical data, you will just see that there is like loss of vegetation, significant, etc. But with radar data, it works differently. Basically, you look at the change in this radar signal, which is affected by mostly like surface roughness and so on. And in case of forests, there are a lot of cases when you can miss the clear cut just because the roughness, which is left after clear cut, some kind of simulates the same radar data, and it's still here. This is a good example, because some examples where you can detect only one part of it and so on. And it's quite complicated, but yeah. On the one hand, for example, in this case, for this particular part, you have radar data from 4 orbits, basically like different sites and so on, and you can combine it together and so on. There is like plenty of ideas what you can test and etc. But at the end, when you go it through, you end up with such kind of graph in this study, and you will end up if we apply radar data, and I believe it's not applicable only to clear cut detection, but in different other change detection applications with radar data, because what it demonstrates, this one is what you want to detect. Basically, in this case, I'm detecting like all 100%, and it's dropping. But if I want to detect like all, and this one is like probability threshold, basically something what I already mentioned, because always you can get out of your model some kind of not only like 1, 0, clear-cut or not clear-cut, but with some kind of probability. Usually in standard, people are using like 0.5. It's again like, it depends like how you can get to this value and what you understand with probability, but it's different matter. But for example, if we would use 0.5, it means we would have this detection accuracy like around 90%, and accuracy of what was the right name for this part of accuracy? Basically, the ones where have no clear cuts, basically negative. I'm just trying to remember now. Basically, another one which shows on the other side how many false positives you have. This one demonstrates false positives. It means, on the other hand, you will have detection accuracy something close to 90, but still you will have something like 50% false positives. In this case, number of false positives was like really large, because clear cuts isn't something what's dominate in the forest landscape, and it means like for some clear cuts you get much more false positives. And of course there is like always like threshold what you can think through, like what could be probability, other things, how to tune. But I believe that in these cases you always will be on this how to say dilemma between how many issues you want to detect and how many false positives you would allow, and so on. And this is again is something what's in my hand. In my head, I think that this is something what you cannot avoid. The next question is how this could be acceptable, and what is from this is acceptable to the end user. And it's again like how to make this bridge between like the end user expectations and needs and what can be achieved from it. Like remember the previous example. And in this case, yes, you always can say that, okay, I don't want to deal with false positives. Okay, we will not deal in this point, but it means we will detect only like 70% of clear cuts. And it's always like a trade-off, like what actually do you want out of it. Another example is related from our study with Greenness Mapping. This is a combination of year-long NDVI data stick, which we believe that really good for representation and quantification of greenness. And this one again is like combination of like multiple year NDVI and looking at trend. And what means red parts means like there is like increase in vegetation in greenness. Red parts shows like some kind of decrease over these years. And this particular example is quite significant one. I think that everyone knows it who is from Latvia. This is IKEA. They start to build it like, I don't know, in 16 or 17. No, 17, I think. And then also you can see how that it, of course, it appears a significant decrease because previously there was like green area. Now there is like shopping mall and parking lot. And there is also some kind of nice relation how it has affected like land surface temperature and created like new small heat island in the city. And then also like interesting application, like how you can apply this parameter on this some kind of units, what are usually people are interested in. It's, for example, in this case, cadastral units, and assess greenness of different cadastral units. But I think this one is even more interesting. This is, by the way, Boulder area, Venice, and in Riga. And these red ones are cadastral units where significant greenness decrease has been detected. Basically, we are analyzing this trend and saying, oh, there's like really significant. And then you can check like what's happening. Like this one is like pretty nice one, large one, where there was like park and there was build a house. Okay, nice. And then was this one. it looks like quite interesting that this is small plot where barely can get like some kind of several pixels in, which I usually have attracted to some kind of. I always like to talk about that you don't want to deal with like border pixels and so on. You want to get rid of them because there is some kind of mixed information inside. But this is quite nice example, which kind of changed my mind because what we can see, there was a tree, single tree, which was disappeared. But this was detected by this approach. And it's quite nice example, which I believe just shows that even if you have Sentinel data, which is not capable to show you like visually, that for example, there is like a tree which is lost, a single tree. But still you can detect it. But of course, there are some kind of limitations if you think through like what could be combinations or causes of 3Ds and so on. But I also just checked like other cases. This one, which already just also shows this, not anymore like black and white, 1 and 0 is 0 not something, but it also shows like probability of negative changes. And here you can see these like high probability spots with red spots, and most of them are like visually can be seen that something has changed and there is some kind of loss. For example, here you can see between like large buildings there is like one tree lost. This one, I think, no, this one. It's not anymore here. And this one example also here, another just I randomly just take, okay, let's check this spot, and you are just surprisingly happy that, oh, it has detected some kind of change and so on. Basically, it shows that, yeah, Sentinel-2 data is useful, for example, for control of some kind of units, like if there is something happening inside and what's even happening. And from spectral data, you can say like what kind of changes these are. At least make some guess, and then someone can go and check like for real cause and reason. Another application which we were involved in this case, which is called our activity Sentilake. This is our project in this already advertised program RPI from ESA. In this project, currently we are collaborating with Latvian Environmental Meteorological Center. And in partnership, we are developing this service for lake water quality monitoring. On one case, it might look quite easy, because what we are doing, you are just taking lakes, looking at the water color and trying to interpret from it like the chlorophyll concentration and making some kind of levels, etc. But the hard part, I would say, it lies over here, this part, because if we use Sentinel-2 data, and for example, for land application, it's quite okay. But when it comes to water application, with water, we get into different problems. Water has like relatively low reflectance. Basically, everything that is from land reflects more light than water. And what does it mean? In this case, you cannot apply standard atmospheric correction approaches, what you are usually using. Like, for example, you get data in SNAP, you're applying atmospheric correction and proceed processing it further. In this case, that will not work. You should look at proper atmospheric correction. Then, for example, you have find proper atmospheric correction. There is another problem. As water reflection is very low, there is influence from the neighbor pixels, basically from the coast. Because there are some, and it always depends on the size of the lake. For example, in case of Burtnieks, yeah, it might be not a problem, it's a relatively large lake, but when it comes to smaller lakes, then this problem appears like more and more and more. And this is something with what you should deal. Basically, to get from color to some kind of assessment of water quality isn't so easy. And there should be some kind of different tricks should be applied. But anyway, if we, for example, compare like even from Sentinel-2 data, like how many observations we can get, yeah, I would say it's quite a decent number in comparison like with reference data amount, what you can get by like physically going and sampling. And there might be you will notice some kind of misalignment between what I spoke before and now. And here I'm stating that we can get like 1 up to 4 Sentinel-2 satellite data observations per month. But previously I just demonstrated you like crop detection, and I said there was no like cloud-free Sentinel-2 data observations. Because in this case, we are not looking at like fully cloud-free scene. In this case, we are analyzing that cloud-free area should be over the lake. And there is also like some kind of threshold and decision, and in which case you decide that it's like it's useful or not useful data scene. But if you go like in such manner, then I would say, yeah, this is something what you can expect per month. And this is another example from another lake, the same, and how, for example, the spike also looks like in the color in the lake, like green stuff in the lake. Another project where I will not go into technical details, but I want to mention like what we are working now on. This one is one of the last like PEX program, which is previously RPI program. In this case, we are collaborating with Preferred by Nature, which is international certification organization. Their interest in this case was certification of sustainable rice growing practice. And to certify rice growers, there is need also for control mechanism. And their interest was how we can improve the effectiveness of control mechanism, implying remote sensing, basically Earth observation. And in this case, what we are trying to solve, the problem that in standard manner, farmers in like in Asia, in this case in Vietnam, they don't care about like water usage. They just flood the fields. It's more safer for them not to lose the yield against pests, etc. But this sustainable practice relies on this, that fields are dried quite frequently just to reduce water usage. And this practice could reach 30% reduction in water use, and also approximately result in 50% reduction in methane emissions. It means like not only friendly for nature, but also for climate. And in this case, yes, the main question is to understand like what practice is managed in the rice field. And there are also like different challenges about which I will not talk. It's not only about like detecting water and so on, but it's more complicated task what we are working on. And this one also is another example of our new activities, which is in collaboration with State Environmental Service. And this is first Latvian project in program of Future EO. We tried and we got this contract, and what the idea of this project is develop approach for remote monitoring of mining sites. It doesn't mean that it will be fully remote monitoring, but basically to get useful information for inspectors who currently are going for checking the activities in mining sites. By on-site visits, but to get useful information that could be used for better planning of on-site visits, and so they can go and already like check all the requirements. And we have gone through the requirement list, and now we are in the process of developing like first data products, evaluating it, and etc., and going further into finding the solution. Which fits both like the user needs and the possibilities of, in this case, yes, Sentinel data. Okay, this was quick. It was not quick, it was quite long, yeah? It was perfect, okay, thanks. I hope this presentation was interesting and you get something useful out of it. And if you have any questions or want to talk, I will be there till the end of the day during coffee break feel free, comment, ask anything. We are quite open also for collaboration if you are interested in. Yeah.
So what we propose to do now, because it's already Friday afternoon, is to split instead of having one long break and then one longer block, to have a 15 minutes break now. Then we will have a short presentation of about half an hour. We can have another 10 minutes, 15-minute break, and then we go with the practical. Does that sound good? And then we can rest a bit more? Okay, so we do now the break until 3:15, and then we're back with the OpenEO platform and the practical.